Rcl Circuits. As the title implies, we could take a resistor and a capacitor and an inductor in parallel across a voltage source. Well, here we have a parallel Rcl circuit indeed. Well, following the rules then for any parallel circuit, we know that the voltage across each component is the same as the source voltage. The resistor voltage, the capacitor voltage, and the inductor voltage would be the same as the source voltage because we do have a parallel circuit here. Well, consequently then, with the same voltage across each component, we only have one voltage, as I said, existing within the circuit. Well, looking at the circuit with respect to voltage, it appears circuit analysis associated with a parallel Rcl network is somewhat easier. Well, in some respects, I suppose this is true. For in this circuit, the only vector we have to concern ourselves with is the current vector. Let's closely look at our circuit once again. And with the applied voltage felt across each component, R, C, and L, we have three individual branch currents, and they are IR, IC, and IL. Now these three branch currents form to combine our total current, IT. Now as you already know or suspected, the total current is not the arithmetic sum of the branch currents, but is the vector sum. Why? Well, let's answer this question by reviewing the current and voltage phase relationship across each component. And we'll begin by investigating the resistive phase relationship. The voltage across and the current through any pure resistive component is always in phase and vectorially represented appears this way. IR in phase with ER. Now note ER represented here would be the same as the applied voltage since we do have a parallel circuit. Our next current would be our capacitive current, IC. We know that the voltage across and the current through any pure capacitive component is 90 degrees out of phase. That is, the current leads the voltage by 90 degrees, such as shown here. IC leads EC by an angle of 90 degrees. Our third current would be our inductive current, IL. We know that the voltage across and the current through any pure inductive component is also 90 degrees out of phase. But the current lags the voltage by 90 degrees and appears this way. IL lags EL by an angle of 90 degrees. Well, from our circuit analysis thus far, it is evident that a current vector is used to represent a parallel AC network. So to show our current vector for this circuit, we need to know the individual branch currents to solve for a typical problem. Well, solving for branch currents by applying Ohm's law in applying the current vectors and plotting these vectors, suppose we assume our resistor 2 k ohms with an applied voltage of 24 volts. Using Ohm's law then, our current would come out to be 12 milliamperes. We would plot this on a vector like this, where IR would be equal to 12 milliamperes at 0 degrees and in phase with EA. Next would be IC, our capacitive current. If we assume a capacitive reactance of 4 k ohms with 24 volts applied across our capacitor, then we will have a capacitive current of 6 milliamperes. And it would be vectorially plotted this way. IC would lead IR by 90 degrees and is equal to 6 milliamperes or 6 units long. Our third current, IL, let's assume we have an inductive reactance of 24 k ohms with 24 volts applied. By Ohm's law, we would then have 1 milliampere of current flowing in. All right, this would appear then on our vector this way, where IL is lagging IR by an angle of 90 degrees, or IL is 1 unit long. Since IL and IC are 180 degrees out of phase, IL can be subtracted from IC and leave a vector sum of 5 milliamperes like this. We can now construct our parallelogram and draw in our current vector, which would appear like this. And if we measured the magnitude of our current vector, IT, it would measure 13 units long, representing a total current of 13 milliamperes. Now we have our phase angle theta generated here. Remember, theta is the angle with which current leads or lags the applied voltage. Well, here's leading. And we could measure this phase angle with a protractor, and it would measure 22, or read 22.6 degrees. This would be plus 22.6 degrees because we have a leading phase angle. Well, fine. Now that we have calculated graphically our total current to be 13 milliamperes and the phase angle to be, as you can see, 22.6 degrees, let's go one step further and find the impedance of our circuit. Once again, we can use Ohm's law. Substituting into the formula, note that the impedance is equal to approximately 1.8 k ohms. Now, although I have chosen to solve for our total current, which is 13 milliamperes, by using a graphic solution, that is, solving for total current by using a graphic solution, we can also use a much more accurate method, and that is Pythagorean theorem in determining our total current. And Pythagorean theorem comes out this way, where IT is equal to the square root of IR squared plus the quantity of IC minus IL squared. We're substituting into this formula then 12 milliamperes for IR, 6 milliamperes for IC, and 1 milliampere for IL. And performing the indicated operation, we can see that 12 milliamperes squared is 144 times 10 to the negative 6. 6 minus 1 is 5. 5 squared would be 25 again times 10 to the minus 6, maintaining our exponent. Adding them, 144 plus 25 would be 169 times 10 to the 6. Remember, when we add, our exponents would remain the same. Extracting the square root then of 169 is 13. Of course, the square root of a negative 6 is negative 3, which would be milli, and our current is, of course, in amperes. So once again, we have determined our total current by using Pythagorean theorem. And our total current again comes out to be 13 milliamperes. What about the angle of our current? Well, we can use the tangent trig function rather than a protractor to determine this angle. And the tangent of angle theta is equal to IC minus IL divided by IR. Substituting into this then, you can see that the tangent of angle theta is equal to 0.4166. Well, looking at our trig table then, we can see 0.4166 is nearest to 0.4163, or the tangent of 0.4163, which once again is 22.6 degrees. So here we have determined our phase angle using our tangent trig function. Well, now that we have calculated our current, once again by Pythagorean theorem, and our phase angle, as you can see, is 22.6 degrees, we can next determine the power dissipated in our circuit, which is the true power, PT. And we can use one of our familiar power formulas. Power is equal to I squared R, since R is the only component in the circuit that dissipates power. Substituting, we can see that our true power is equal to 288 milliwatts. Now, as in any reactive circuit, we also have another power, and that is the apparent power, PA. And that is equal to the applied voltage times the total current. Substituting into this formula, you can see we have 312 millivolt amperes of apparent power. Now recall, apparent power is the power delivered to the circuit by the generator. With this, then, we can then determine the efficiency of our circuit, or better known as the power factor. And we know that the power factor is always equal to the cosine of the phase angle. Well, the cosine of 22.6 degrees, by looking at our trig table, we can see is 0.9232. Cosine of 22.6, you see, 0.9232. So once we have determined our phase angle, we also know our power factor simply by taking the cosine of the phase angle, which is 0.92. Another relationship for power factor is the ratio of true power to apparent power. Substituting into this formula, we can once again see that our power factor is the same, 0.92. Now also in Formula 2, if you know any two quantities, you can always solve for your third unknown, sort of like Ohm's law. Simply transpose your formula and then solve for that third unknown quantity. Well, throughout the lesson, I have been using a circuit to obtain a resultant current vector like this one, where IC is greater in magnitude than IL. This being the case, our total current leads our applied voltage by the phase angle. And as I said, IC would have to be greater than IL. Well, with a condition such as this, our circuit is acting capacitively because we have a leading phase angle. But suppose now I wanted our circuit to go from a leading phase angle down to a lagging phase angle. Well, to cause this to occur, then IL would have to be greater in magnitude than IC. And what circuit change could we make for this to occur? Well, to illustrate this point, I have a little demonstration set up. I have a parallel AC network similar to the one we have been using here in this lesson, only I have each current in each branch metered. That is, our capacitive current, IC, our resistor current, IR, and our inductor current, IL. Now I have the circuit, as I said, connected to a variable frequency source where I can vary the frequency applied to this network. Well, suppose we decrease the frequency applied to our network. What do you suppose is going to happen to IC, IR, and IL? Well, let's analyze the situation first and determine what's going to happen. We know if we decrease the frequency applied to our network, the capacitive reactance of the capacitor is going to increase. Therefore, IC will have to decrease. Likewise, when we decrease the frequency, we're going to decrease the inductive reactance of the coil, and I sub L would have to increase. But what about IR? Does frequency have anything to do with R? No, it doesn't. The only thing that's going to change the current through R is the voltage applied to the circuit. And since we are not changing the voltage, IR should and will remain the same. Well, now I want you to observe these meters closely. I'm not so much interested in determining the actual value indicated on the meter as I am for you to watch the action between the meters. Now observe IC and IL and IR as I decrease the frequency applied to the circuit. Note, as I decrease the frequency, IC decreased, IL increased, but what happened to IR? The value of IR remained exactly the same. It did not change. Well, we determined that previously, that it wasn't going to change. Well, this condition would now be represented vectorially like this, where IL is greater in magnitude than IC. We now have a lagging phase angle. Remember, IL is greater than IC. This being the case, then, our circuit is now acting inductively. So it is this action, by changing the frequency applied to the circuit, that causes IC to increase and IL to decrease. And by decreasing frequency, the reverse takes place. But note the position of IR. As I increase and decrease frequency, IR remains the same, and the circuit either acts capacitively or inductively.